Right. So first of all, thanks to the organizers, Felix and Claudio and all the others for the invitation. What I'm going to do is indeed to give you a sort of an outline of a particular formalism for quantum gravity. It relates closely to both the perspective and formalism discussed by Renata this morning and the one by Thomas as well. But it may not look like at first sight, so because I will take a different perspective on it. And I will try to highlight the points of connection and maybe some points of difference, but you're very much welcome to ask for more details. Second, I will not build the formalism step by step in a mathematical way because it will take too long. So I will try to stay a bit on the surface of things and highlight the key aspects. And again, you're very much welcome to ask for more details at the mathematical or physical level. Good. So that's one definition of quantum gravity. And this is what this formalist tries to do, to give you a quantum description of supposedly more fundamental building blocks of space-time. And although it's not a direct quantization or general relativity in the sense that Thomas explained for the canonical approach and Renate discussed for the lattice covariant approach, it tries to incorporate some key lessons from classical general relativity to take them very seriously. So what are those lessons? Well, there are many, but one is that the gravitational field is space-time geometry, and most important, it's a dynamical physical entity. So it's the physical system we are trying to deal with is space-time itself. Which means, in practice, apart from all the conceptual aspects, that you cannot rely in your construction of a theory of quantum gravity on any given space-time and geometry. These are the objects you want to explain, you want to reconstruct, you want to deal with dynamically. The second main lesson has to do with diffeomorphism invariance of classical general relativity. Renate discussed that as well. So, although we formulate physics and general relativity in particular in terms of fields defined on some smooth manifold, we know, because of the gauge symmetries of the theory, that that supporting smooth manifold is a sort of an auxiliary redundant structure. We should not expect it to find it in the fundamental theory. This also implies that observables in the theory at the fundamental level, but in fact this is true also in classical GR, cannot be localized on the manifold. Anything that depends on a particular point on the manifold is not itself gauge invariant. It's not itself a physical observable of the theory. Does it mean that observables in GR and then quantum general relativity and quantum gravity are non-local? Well, if by locality you mean localized with respect to the manifold, yes. And Renate discusses how you have to take integrals and over the full space-time manifold, over the full manifold of local scalars, to have a diffeom-invariant quantity. But we do local physics all the time. But if you analyze what we actually do, we localize systems with respect to space-time, but as defined in terms of physical frames. So one part of the story will be in the fundamental theory to find the analog of this type of construction, to introduce degrees of freedom that you can use as physical frames and define what you mean by space-time localization with respect to them, and then find their effective dynamics. Also, I'm staying at even more general level than the already general talk I'm supposed to give. You can take two attitudes with respect to what we had to do to get to a more fundamental theory. You can just say, okay, I have a classical theory, which is general relativity, and I quantize it. I can quantize it canonically, covariantly, with lattice methods, and so on. And it's all good, if we can do it. Or you can say, well, what I'm really interested in is some other candidate fundamental degrees of freedom from which the metric, the other fields emerge as collective entities. And so the fundamental quantum theory of these new degrees of freedom may not be the result of quantizing the classical theory. Now, it's two different perspectives. At the technical level, I have to say that to a large extent, it doesn't make too much of a difference which perspective you take, because the very moment you use, I don't know, lattice structures, whether you interpret them as regularization tools or new degrees of freedom, you still have to take collective dynamics, continuum limits, coarse graining to recover geometry in space-time as we know it. So at the technical level, many things, well, are very similar. Of course, the way you take continuum limits and what you hope to achieve in terms of what sort of phase transitions, what sort of signatures of the underlying degrees of freedom you want or not will depend on your perspective. We will see some example later. Okay, so I'm taking in the following this second perspective of an emergent space-time. And the last point I want to emphasize is that it's a pretty radical one, because you don't want just curvature and gravitational interaction and deviations from flat space physics to emerge. It's not just emergent gravity, it's emergent space-time. So a flat space-time, from the point of view of the formulation of this new, more fundamental candidate degrees of freedom, is itself a highly collective emergent object. Okay, so enough for conceptual ingredients. Let me say more about the formalism. So this is an entirely biased and perspective of the formalism I'm taking. You should see it just as, in fact, describing the perspective, meaning, from my perspective, sitting in the blue box, it's amazing that we can find a lot of connections to other quantum gravity formalisms. You should not interpret it as, well, if you start from any of the other boxes, you necessarily have to go to the blue box. I wish that was true, but unfortunately, I don't think it is. Anyway, the tensorial group field theory formalism is, in fact, incorporating or connecting in different ways with the mathematical structures and some of the conceptual insights and results obtained in other quantum gravity formalism. And for me, this is a nice thing. In one slide, the basic idea. You have seen how you can replace physics defined on a smooth manifold with physics defined in terms of lattice structures. And there I illustrate how you can replace a smooth ball with a triangulated one in 3 dimensions. This triangulated ball is made of building blocks, which are simplicial in this particular lattice rewriting. You can consider all these building blocks individually and collectively, but as the focus of your attention. These are the sort of quanta, atoms, building blocks from which we want to reconstruct space-time. And this formalism, tensorial group field theory, is a quantum field theory, of course, more abstract than the usual ones we are used to define on a supporting space-time manifold. It's a field theory that deals with the creation and annihilation processes of these building blocks, and how from these building blocks you can reconstruct extended structures with the geometric first and then gravitational interpretation. So that's the basic idea. There are quantum field theories of a more abstract type that whose atoms or quanta are abstract simplices rather than particles moving in a given space-time manifold. So they are, from this perspective, a quantum field theory of space-time, of geometry, not defined on a space-time on some given geometry, like usual quantum field theories in particle physics and so on. Okay, so now I give a bit of the ingredients of the formalism, and I encourage you to take them as a sort of ingredients that you have to provide me from your favorite quantum gravity formalism, regardless what it is, because to a large extent, it is just the basic structures that any candidate quantum theory of gravity should provide. So this tensorial group field theory will be an example of a number of steps you have to take and to convince me that you have a candidate theory of quantum spacetime. Okay. The focus is on this quantum tetrahedra. You can have a move. Yes. Okay. You can have first of all, you can deal with the simplest of the objects, a single tetrahedron in flat space, Lorentzian Minkowski's flat space. You can write down the classical phase space variables that will allow you to talk about this geometry and extrinsic curvature in the embedding Minkowski space. You can write down the classical simplicial geometry. You can show that a good embedding phase space is this cotangent bundle of 4 copies of SU2, and you just have to add constraints, geometric conditions on the variables in this phase space to be able to capture all the geometric properties of this super simple object, a simple tetrahedron. So what are the properties? Well, you want to be able to talk about edge lengths, the volume of the tetrahedron, angles, and the areas of the triangles. I mean, quite simple. So Euclidean geometry for a single tetrahedron. You have some classical phase space. The choice of variables and the choice of phase space is adapted, of course, to what I want to do next. So there are other formulations you can think of classical simplicial geometry, but these are convenient ones. You can give a more covariant formulation in the same algebraic language in terms of the cotangent bundle of the Lorentz group instead. But again, it's an algebraic formulation of the classical geometry of a single tetrahedron. From that, you can quantize. You have a phase space for a single tetrahedron and its geometry. You can quantize that phase space, choose your favorite method. You can proceed just by geometric quantization of the simplicial structure, but if you know about canonical loop quantum gravity, you can realize that what you're doing is take the simplest building block of the quantum states of geometry in canonical loop quantum gravity. So of course, I'm skipping all the steps, but you can do that. You end up with a Hilbert space for a single tetrahedron, described in purely algebraic variables taken from the representation theory of SU2, if you started from that phase space, or from the Lorentz group, if you use the more covariant one. And they are equivalent. I mean, dynamically, they can be equivalent. If you have a phase space, you can have different unitary equivalent representations of the states, of the wave functions in this Hilbert space. And they're related by the group theoretic generalization of Fourier transform. Peter Weil, if you're doing SU2 representation theory, or the Plancherel decomposition if you're doing Lorentz representation theory. Which means that you have your wave functions are either functions on the group manifold, half of the phase space, or functions on the cotangent space to that group manifold, the momenta, which are, well, in this formulation, they are the representations of the group, labeled by representations of the group. In the same sense in which when you do Fourier analysis in flat space, you can either write your functions, your wave functions for a single particle as functions of the position in flat space, or functions of the representations of the translation group, which are the momenta. You can extend this construction from a pure geometric tetrahedron to a geometric tetrahedron, which also has sitting on top of it some discretized scalar field. Just like you discretize geometry and you think of a simplicial building blocks, you can have a discretized scalar field, which is nothing else than a real number at each tetrahedron. If you think of discretizing a smooth manifold, you have chunks. A smooth scalar field will be a smooth distribution of real values across the manifold. In the discrete setting, it's just a particular real number at each tetrahedron. So you can generalize the construction in that case to several scalar fields, and this will be useful later on for the relational construction of observables. I have spoken only about individual tetrahedra. You can take as many as you want, and you can construct, once you have the Hilbert space for a single tetrahedron, you can construct a Fock space for arbitrary collections of quantum tetrahedra. Again, think of the tetrahedron as your quantum, your atom, your particle in the analogy, and you have a Fock space for that. This will be the kinematical Hilbert space of the theory. And you can use, you can adopt conveniently a second quantized language in terms of creation and annihilation operators that create out of the Fock vacuum 1 tetrahedron, 2 tetrahedra, 4 tetrahedra, the Avogadro number of tetrahedra, and so on, or annihilate them. Fock space, second quantized language. Of course, even the simplest discretization, triangulation of a given extended manifold will require several tetrahedra glued together appropriately. What's the gluing? It turns out that in this construction, gluing two tetrahedra is imposing maximal entanglement among some of the degrees of freedom of the two quantum tetrahedra, and the geometric interpretation of that, which can be corroborated by the computation of geometric quantities, is that you have glued two tetrahedra across a face. And you can do this gluing to construct arbitrary, large, connected simplicial complexes, quantum simplicial complexes. The dual picture is that you can take a vertex at the center of each tetrahedron, and when you do the all gluing, it's like having a graph with several vertices and connecting links between any two of them. That, with the algebraic data I illustrated in the previous slide, is what is called a spin network, and is indeed the typical quantum state in canonical loop quantum gravity. So this is sort of a second quantized reformulation of some of the structures and ideas of canonical loop quantum gravity, on top of being obviously a different way of doing lattice quantum gravity. We'll see that connection in a second. You have a Hilbert space, you have the classical phase space observables, you quantize also those observables, and you can work with the operators acting on the Fock space, which correspond to, say, the total volume of your collection of tetrahedra, the total number operator. If you have scalar fields, the average quantity or the average value of your scalar field, or the momentum of the scalar field. These are all quantities you can define at the discrete level and then second quantize. These, of course, are the type of quantities you need in order to make any statement about the effective dynamics of the theory matches or doesn't match what I would get for the same observables in continuum generativity in some appropriate limit, which I will get to in a second. Okay, this was the kinematics. The Fock space of states, the operators that act on it. What about the dynamics? Of course, there's no single dynamics because what I illustrated is more of a formalism with a certain restriction on the type of quantum states I'm interested in. Any specific model of dynamics will correspond to a particular choice of actions and partition functions for the field theory that I'm interested in. So everything else will become model dependent. What is generic? Several things are generic in this class of models. One is that we focus on models which have the following property. When I look at the Feynman diagrams in a perturbative expansion of the dynamics, of the quantum dynamics. The Feynman diagrams representing creation and annihilation processes of quantum tetrahedra are in fact topologically equivalent to simplicial complexes in one dimension higher. I started from tetrahedra. They have to evolve in some additional dimension. Take that with care. And the diagrams, the interaction processes that these tetrahedra have, can be mapped topologically to simplicial complexes in 4 dimensions if I started with the 3-dimensional building blocks. And you can rescale if I'm interested in models of 2-dimensional gravity, 3-dimensional gravity, and so on. And these are constructed taking the building blocks of the processes, which are the interaction vertices, as 4-dimensional simplices, and then gluing them in all sorts of ways, as you would do in any Feynman expansion, perturbative Feynman expansion in a field theory. This is just to scare you, is a particular model written in a particular representation, just to show you that the fact that you want this highly non-trivial combinatorial structure in the interaction processes requires that your action, in particular the interaction vertices, has a highly non-trivial combinatorial structure in the algebraic data, because you want to label the 4 simplices and it has to have the combinatorics of a 4 simplex. But okay, this is just to say that I use the words, but if I'm really forced, I can use the math. And then any given model will be an assignment of an action. You choose, you tell me where you come from, if it is from lattice quantum gravity, from canonical loop quantum gravity, from God has spoken to you directly and told you what the model of the universe is. Whatever is your source, you choose a model, which means you choose some action, which has to have some peculiar combinatorial structure, as I said. Then you can write down the partition function of this abstract field theory, expand it in diagrams, and what I just said becomes true, meaning you can expand in Feynman diagrams and you realize that the diagrams are dual to cellular complex, and because you glue them in all sorts of ways, you glue simplices in all sorts of ways, you get this expansion over all possible simplicial topologies. So there is a sum over topologies involved by construction in this type of models. And the problem will become to control that. Or if you're more of a mathematician, to actually define it mathematically. But the construction principle should be clear. And then the other thing that it becomes model dependent, but is pretty generic, is that for models with the quantum geometry interpretation I've given in the previous slides, what is true is that the amplitudes, the Feynman amplitudes you associate to each lattice produced by the expansion, takes the form of a lattice gravity path integral of the type, but with some additional data, of the ones that Renate discussed this morning. So for each Feynman diagram, the amplitude that this type of models assign can be related to having taken continuum gravity, discretized it on a lattice, and having written the exponential of the action with some choice of measure. Okay, for each of the diagrams. And here we have a sum over all the triangulations, again, very similar to what Renate was discussing, extended to topology changing processes, because you cannot do otherwise in a Feynman expansion. Okay, and of course, if you're able to resum to define the full or compute the full partition function, you have taken the full continuum limit, because you've summed over infinitely refined complexes, if you're able to do it. Okay, and this is just one example of a model in 3 dimensions, so 2 plus 1, where you write down an action which is, apart from the combinatorial structure, really straightforward, just a bunch of delta functions relating the arguments of the fields. So it's a very simple model. Still, when you write down the Feynman expansion and you look at the Feynman amplitudes, you can show directly that they take the form of a discrete first-order path integral for 3D gravity. This is a Euclidean model, so it's pretty simple. But this is exactly what you could have started with. You could have said, I take three-dimensional continuum gravity in first-order variables. I discretize on a lattice. I write the exponential of the action with the natural choice of measure, and you would have written down this for each lattice. Here it is produced as a Feynman amplitude. Right? This could be a nice construction, but we want to take a continuum limit. Not because necessarily the continuum physics is the right one, but because it's the one we are used to and because it's how we do physics. So we want to connect with everything we know already and be able to make predictions about any novel effect. So this is something you had to do if you're a physicist. If you're a theologian, then no. You can just say, well, the world is discrete. I only care about the discrete theory. But okay, they pay me to do a different job. So what is the continuum approximation? How we try to extract continuum limit? There is a formal aspect, computing the continuum limit of the quantum dynamics. And then there is a physics aspect, extracting an effective continuum dynamics that you can compare with GR. The formal one. These field theories can be studied as field theories. We have another expert here, Vincent. You can take them and they're just cute, peculiar, challenging new types of field theories. So you can do perturbative, non-perturbative renormalization, constructive renormalization. You can do all sorts of stuff. It's not what I'm going to talk about. What you care is, again, some effective coarse-grained description of the system. Or at technical level, you would like to be able to compute the full sum or the full partition function of the field theory. What is the simplest approximation you can think of a partition function that somehow is already fully continuum from the point of view of the lattice structures that appear here? Well, it would be the mean field approximation of the partition function. So you can take that. Of course, it's the most drastic, I was about to say stupid, but the most drastic approximation of the full quantum effective action that would correspond to the full continuum quantum dynamics of the theory. But you also know that you can expand around the mean field and then you add corrections. So you do that. So in the following, I will just discuss what sort of physics we see in this mean field approximation. What I want to stress is that if you step back a second and you look at the same approximation from the point of view of the sum over all the triangulations with lattice structures and lattice gravity path integral, this is a highly non-perturbative quantum approximation. So mean field is classical from the point of view of the field, which is a collective observable. It's highly quantum from the point of view of the atoms or the quanta. This may be a bit subtle, but if you think of examples you should know already, like classical electromagnetism, it's obvious. So more concretely, even approximating the partition function at mean field or the effective action at mean field means having implicitly resummed an infinite number of triangulations, the three-level ones, whatever the exact definition of three-level in this context. So from the point of view of the sum over triangulations, you resummed an infinite series up to infinite refinement in one go. And I agree with Renate that if you want to actually take the sum and do it, you have to resort to numerical simulations. It's not something you can actually do one by one analytically. But here you can bypass that type of challenge by using the field theoretic formulation of that sum. The second point, the mean field approximation corresponds, if you know about Bose-Einstein condensates, to assuming that the actual ground state of the theory is at least close to the exact condensate in which all the atoms have the same wave function, which corresponds to the mean field. Of course, it's not a realistic assumption about the ground state, but we also know from our friends in the experimental labs that it does work. there are physical regimes in which that is a decent approximation to the full quantum interacting theory of a large number of atoms. But again, from the point of view of the simplicial building blocks, is implicitly having superposed an infinite number of them. Something that if you try to do, one by one analytically without other truncations, it's simply impossible. Okay, now this is sort of for the mathematics. We look for this approximation that bypasses the explicit resummation of states and dynamical processes and uses heavily the field theoretic formulation. What about the physics? We want to reconstruct some effective physics. We need observables, as Renat has emphasized. So the mean field dynamics has a couple of very general properties that guide towards the physical interpretation of the effective dynamics. The first one, the mean field itself for these quantum geometric models in which you have the quantum tetrahedra and so on, has the following property. The domain of the mean field can be shown to be isomorphic, in fact is diffeomorphic, to the space of spatially homogeneous geometries. It's a mathematical fact that I can intuitively justify and explicitly show, but the point is that at the end of the day, the mean field dynamics is an equation of motion for a function, a complex function on a domain which is mini-superspace, the space of homogeneous geometries. The same type of dynamical variable that you have in quantum cosmology, where you quantize the symmetry-reduced sector of GR, if you know about that. Okay, so this means that at this mean field approximation, you should at least be able to capture cosmological dynamics, the dynamics of cosmological observables. The second point is that the equation of motion that you get at mean field level is a nonlinear equation for such a function on mini-superspace. So it's literally, mathematically, a nonlinear extension of the type of equations you would get from quantum cosmology in this more traditional sense. And again, this is generic. Is the only thing you need, whatever model you start from, the only thing you need is that you have proper quantum geometric data for your building blocks. So you can rewrite in a more convenient language. And then what you do is to take the observables you introduced earlier, like the volume of the universe, the values of scalar fields and so on average, the global version of those quantities, and somehow write them relationally. So compute observables, I'm skipping of course the details, that get the interpretation of the volume of the universe when the scalar field you have takes a particular value. You are effectively using a scalar field, for example, as a clock that defines your time. So take the volume at a given value of time defined by the scalar field as your observable and extract an effective dynamics for that. You're going to have an equation for the volume of the universe evolving in time, and that's what you want to compare with general relativity. You can do that, so you can really start from the fundamental theory and its observables and extract an effective continuum dynamics for observables with a proper geometric gravitational interpretation. And then, okay, there are many results. It's a lot of people working on that by now. You can show, for example, that in a large variety of models, when the volume is small at early times, you don't get the singularity and you get, in fact, a bounce replacing it. So it's like a bouncing cosmology that you get. At larger volumes and later times, you recover the Friedmann equation with the simple matter content that we used. And in fact, you can reproduce the dynamics derived from quantum cosmology, from loop quantum cosmology, as a particular case. Then things become even more interesting when the volume starts expanding, because at larger volumes, the dynamics is more complicated, but it seems that with a lower degree of generality, but still not with extreme fine-tuning, the interactions of the atomic building blocks produce an acceleration of the volume expansion. And in fact, you can show that this type of expansion can be produced at early times, but again, there you have to be a little bit more careful what type of models you work with. But there is the possibility of both a dark energy and an inflationary phase produced just by quantum gravity interactions. You don't need to add any additional degree of freedom, like a scalar field with special potentials. And then you can extend the whole analysis to inhomogeneities and so on. So in principle, here was the moment to give you some general lessons that we learned from all of this about emergent spacetime and so on. But my time is up. And so I thank you for your attention, and I'm happy to answer questions.